This is a bonus video for Lecture 2.4, Evaluating Proofs. In this video, we will analyze proofs and assess whether the argument is correct or incorrect. When evaluating the correctness of a proof, our goal is to identify the logical errors if there are any. The following are examples of logical errors. Using the incorrect proof structure. Recall that the proof structure depends on the underlying propositional formula of the claim. Using a proof outline that does not correspond to the propositional formula of the claim produces a proof that is logically incorrect. Stating an invalid assumption. The assumption is the starting point of the argument. So if this is incorrect, the entire proof structure is incorrect. Making an invalid conclusion or inference. This means stating a conclusion that does not follow logically from earlier statements in the argument. This would make the entire argument invalid. Note that the following are not logical errors. Lack of detail. In many cases, we omit details which are deemed to be trivial or too elementary. Sometimes, the lack of detail makes the proof difficult to read and understand. However, this may also mean that the intended audience already has a certain level of familiarity with the material. It is always best to provide as much detail as we can. However, a proof may still be correct even if some details are omitted. Unstated assumptions. One case where this is not an error is if it is clear from the context of study that these conditions are assumed to always hold. It should be clear from the way that the proof is written that these assumptions form the basis of the argument. The examples that we shall show in this video use concepts from high school algebra. We shall take the following as facts. Some of these have been proved in previous exercises using axioms of real numbers. For any real numbers x and y, the following are equivalent. X is positive, 1 over x is positive, and minus x is negative. Likewise, the following are equivalent. X is negative, 1 over x is negative, and minus x is positive. The product xy is equal to 0 if and only if one of the factors is 0. The product xy is positive if and only if both factors have the same sign. The product xy is negative if and only if the factors have different signs. For any real number x and any positive real number a, the absolute value of x is defined as follows. It is equal to x if x is non-negative and equal to minus x if x is negative. The absolute value of x is equal to a if and only if x is either a or minus a. The absolute value of x is less than a if and only if x is less than a and x is greater than minus a. We write this as minus a is less than x is less than a. Note that the continued inequality is valid because minus a is less than a since a is positive. The absolute value of x is greater than a if and only if either x is greater than a or x is less than minus a. Note that we do not write this as a is less than x is less than minus a, since a is not less than minus a. Assume throughout that all variables are real numbers. For our first claim, we have the following. If x squared minus x is greater than 2, then either x is less than minus 1 or x is greater than 2. Pause the video now and read the proof carefully. Assuming that you have read the proof, let us now begin our analysis. First, observe that the claim is a conditional statement with antecedent x squared minus x is greater than 2 and consequent either x is less than minus 1 or x is greater than 2. Next, we will get the outline of the given proof. To do this, we need to identify the starting point and end point of each part of the argument. Observe that the first sentence is a statement of a fact that will be used later in the arguments. It is not the starting point of the argument, so we can omit this from the outline. Likewise, the last sentence is a recap of what has been proved. It is not the end point of the argument, so we can also omit this from the outline. Let us look at the second paragraph. The second paragraph begins by assuming that x is greater than 2 and ends with a conclusion that x squared minus x is greater than 2. Hence, this paragraph shows that x squared minus x is greater than 2 whenever x is greater than 2. The third paragraph begins by assuming that x is less than minus 1 and ends with a conclusion that x squared minus x is greater than 2. Hence, this paragraph shows that x squared minus x is greater than 2 whenever x is less than minus 1. The statement proved by the argument is the conjunction of the two conditionals if x is greater than 2 and then x squared minus x is greater than 2. And if x is less than minus 1, then x squared minus x is greater than 2. This is equivalent to the conditional if either x is greater than 2 or x is less than minus 1, then x squared minus x is greater than 2. This statement is the converse of the claim, which is not equivalent to the claim. Therefore, the proof is incorrect. Let us now consider another proof of the same claim. Pause the video now and read the proof carefully. Assuming that you have read the proof, let us now begin our analysis. The proof begins by saying, assume x squared minus x minus 2. The expression x squared minus x minus 2 is not a sentence and hence cannot be used as an assumption. This counts as an invalid assumption. Hence, this proof is incorrect. Suppose that we replace this with a statement, note that x squared minus x minus 2 equals x plus 1 times x minus 2. This is now a complete sentence. We can now proceed to analyze the structure of the proof. The first sentence states a fact that will be used in the argument. It is not the starting point of the argument. Hence, we omit this from the outline. Similarly, the last sentence is a recap of the statement that was proved. It is not the end point of the argument, so we also omit this from the outline. The argument in the first paragraph begins with a statement x squared minus x is greater than 2. It concludes that this is equivalent to the statement both x1 and x2 and x plus 1 and x minus 2 are positive, or both x plus 1 and x minus 2 are negative. Notice that this is a disjunction. Also, if we read the details, we see that the justification of this conclusion is correct. So the first paragraph begins by assuming that x squared minus x is greater than 2 and shows that this is equivalent to the condition that either both x plus 1 and x minus 2 are positive or both x plus 1 and x minus 2 are negative. The second paragraph begins with a statement both x plus 1 and x minus 2 are positive. It ends in the statement either x minus 1, x is less than minus 1, or x is greater than 2. Moreover, if we examine the details, we see that the argument is valid. So the second paragraph begins by assuming that both x plus 1 and x minus 2 are positive and shows that either x is less than minus 1 or x is greater than 2. The third paragraph begins by assuming both x plus 1 and x minus 2 are negative. It ends with the conclusion either x is less than minus 1 or x is greater than 2. Moreover, if we read the details, we see that the argument is valid. So the third paragraph begins by assuming that both x plus 1 and x minus 2 are negative and shows that either x is less than minus 1 or x is greater than 2. Notice that in the second and third paragraphs, the assumptions are different but the conclusions are the same. Based on the outline, the statement proved in the second and third paragraphs is the conditional statement if either both x plus 1 and x minus 2 are positive, or both x plus 1 and x minus 2 are negative, then either x is less than minus 1 or x is greater than 2. By the argument in the first paragraph, the antecedent of this conditional statement is equivalent to the condition x squared minus x is greater than 2. So the statement proved is the conditional sentence if x squared minus x is greater than 2, then either x is less than minus 1 or x is greater than 2. This is precisely the claim. Furthermore, since the details of each part of the argument are correct, the proof is correct. Notice that this proof, although valid, does not follow the proof outline for the propositional form of the claim that we described in Lecture 2.1. In the next slide, we will show a proof that follows the prescribed proof outline. We still begin by assuming that the antecedent x squared minus x is greater than 2 holds. Since the consequent is a disjunction, we shall assume as well the negation of one of the conditions in the disjunction. Hence, we also assume that x is greater than or equal to minus 1, or alternatively, that x is less than or equal to 2. We need to show the remaining condition in the disjunction. So if we assume that x is greater than or equal to 1, then to minus 1, then we need to show that x is greater than 2. Alternatively, if we assume that x is less than or equal to 2, then we need to show that x is less than minus 1. Here is the proof. Assume that x squared minus x is greater than 2, and x is greater than or equal to minus 1. Note that the condition x squared minus x is greater than 2 implies that x squared minus x minus 2 is greater than 0, which, by factoring the quadratic polynomial, is equivalent to the condition that x plus 1 times x minus 2 is greater than 0. So either both x plus 1 and x minus 2 are positive, or both x plus 1 and x minus 2 are negative. In particular, x plus 1 cannot be 0. Now, the assumption that x is greater than or equal to minus 1 implies that x plus 1 is greater than or equal to 0. Since x plus 1 cannot be 0, it follows that x plus 1 is positive. Thus, x minus 2 is also positive. Therefore, x is greater than 2 as required. This completes the proof. Observe that this proof is shorter than the one in the previous slide. This shows the advantage of following the proof outline described in Lecture 2.1. For our second claim, we have the following. If either x equals minus 1 or y equals 1, then xy minus x plus y equals 1. Pause the video now and read the proof carefully. Assuming that you have read the proof, let us now begin our analysis. The claim is a conditional sentence whose antecedent is the disjunction either x equals minus 1 or y equals 1, and whose consequent is the statement xy minus x plus y equals 1. The first paragraph starts by assuming that x equals minus 1 and y equals 1, and ends with a statement that xy minus x plus y equals 1. So the first paragraph assumes that x equals minus 1 and y equals 1 and shows that xy minus x plus y equals 1. The statement proved in the first paragraph is the conditional statement whose antecedent is the conjunction x equals minus 1 and y equals 1, and whose consequent is the statement xy minus x plus y equals 1. Note that this is not equivalent to the claim. This is used in the second paragraph to deduce the claim. Let us check if the remaining argument is valid. The first sentence of the second paragraph is the sentence, if both x equals minus 1 and y equals 1, then either x equals minus 1 and y equals 1, or y equals 1. We know that this is a tautology. Hence, it is valid to state this. The last sentence is the claim itself. Thus, the argument in the second paragraph has the premise: if both x equals minus 1 and y equals 1, then xy minus x plus y equals 1. And if both x equals minus 1 and y equals 1, then either x equals minus 1 or y equals 1. Its conclusion is, if either x equals minus 1 or y equals 1, then xy minus x plus y equals 1. The argument has the underlying formula. P implies Q and P implies R. Therefore, R implies Q. We see that there are two logical errors here. First, the assumption x equals minus 1 and y equals 1 is neither equivalent to nor follows from the antecedent of the original claim. Hence, this is an invalid assumption. This is the first logical error. We can show that the propositional formula, if P implies Q and P implies R, then R implies Q, is not a tautology. Hence, the argument in the second paragraph is invalid, which means that the conclusion that the claim holds is invalid. This is the second logical error. Therefore, the proof is incorrect. Let us give a correct proof for this claim. Since the antecedent of the claim is a disjunction, we will give a proof by cases. For the first case, we assume that x equals minus 1 and show that xy minus x plus y equals 1. For the second case, we assume that y equals 1 and show that xy minus x plus y equals 1. If x equals minus 1, then by direct substitution, we see that xy minus x plus y equals minus y plus 1 plus y, which is equal to 1. Likewise, if y equals 1, then by direct substitution, xy minus x plus y equals x minus x plus 1, which is also equal to 1. This proves the claim. Let us look at a third claim. The statement is, for any real number x not equal to minus 1, there exists a real number y, such that xy equals x minus y. Pause the video now and read the proof carefully. Assuming that you have read the proof, let us now begin our analysis. The claim is a quantified statement of the form, for all x in R not equal to minus 1, for some y in R, xy equals x minus y. Since the phrase for all x in R not equal to minus 1 is stated first in the claim, a direct proof should start first by letting x be an arbitrary real number not equal to minus 1. This is indeed the first sentence in this proof. Since the phrase there exists some y in R comes next, a constructive proof should give a specific number y. In this proof, y is defined to be the number x minus xy. Although the second step is correct, there is a problem with the way that y is defined. In particular, the definition of y contains the symbol y. This makes it a circular definition, that is, a definition which relies on the concept being defined. A circular definition does not give us any information on the concept being defined. In the case of defining y as x minus xy, this means that the unknown number y can only be obtained by taking the expression x minus xy, which is impossible since we still do not know what y is. This is an error in the proof. Therefore, the proof is incorrect. Let us consider a second proof for the same claim. Pause the video now and read the proof carefully. Assuming that you have read the proof, let us now begin our analysis. The first sentence is still, let x be an arbitrary real number not equal to minus 1, which is appropriate for the universal quantifier. The second sentence defines a specific y, which is appropriate for the existential quantifier. This time, the expression for y does not contain the symbol y. Given any x, we can always get y. This means that this definition is not circular. The next two sentences prove that y is a real number, which is one of the conditions required for y. This step is correct. The last step that needs to be done is to prove that y and x satisfy the condition that xy equals x minus y. However, notice that the next part of the proof begins with the statement xy equals x minus y. As written, the statement xy equals x minus y is used as an assumption. This is wrong, since xy equals x minus y should be the conclusion of the argument. Hence, this is an invalid assumption. Because of this, the proof is incorrect. Let us consider a third proof of this claim. Pause the video now and read the proof carefully. Assuming that you have read the proof, let us begin our analysis. After letting x be an arbitrary real number not equal to -1, which is the correct first step, the proof proceeds to consider three cases. Although it is not written down, the fact that is implicitly used here is the trichotomy axiom of order applied to the numbers x and 0. Notice that the assumptions in each case coincide with the three possible relationships between x and 0. Each possibility is considered in a case, so the cases are exhaustive. Let us get the outline of the argument in each case. In case 1, after assuming that x equals 0, the number y is taken to be 0, which is clearly a real number. Then it is showed that the product xy is equal to x minus y. The last sentence is just a statement of what has been proved, so we can omit this from the outline. Thus, in case 1, we begin by assuming that x equals 0, take y to be 0, then show that xy equals x minus y. In case 2, we assume that x is greater than 0. We take x to be 1 and y to be 1/2, which is clearly a real number, and show that for these values, xy equals x minus y. The last sentence is a recap of what has been proved, so we may omit this from the outline. Thus, in the proof of case 2, we begin by assuming that x is greater than 0, take x to be 1 and y to be 1/2, then show that xy equals x minus y. Finally, in case 3, we assume that x is less than 0 and not equal to -1. We take x to be -2 and y to be 2, which is clearly a real number, and show that with these values, xy equals x minus y. The last sentence is again a recap of what has been proved, so we omit this from the outline. Thus, in the proof of case 3, we begin by assuming that x is less than 0 and not equal to -1. Then take x to be -2 and y to be 2, then show that xy equals x minus y. Notice that in case 2, x is taken to be a specific positive number, and in case 3, x is taken to be a specific negative number not equal to -1. This means that, for each of these cases, it is proved that the condition holds only for one specific value of x. It does not follow that the conclusion holds for all values of x that satisfy the hypothesis of the case. This means that the proof is incorrect. Let us now show a correct proof for this statement. We begin by letting x be an arbitrary real number not equal to -1. Then, we give a specific number y, verify that y is indeed a real number, and that x and y satisfy the equation xy equals x minus y. Here is the proof. Let x be an arbitrary real number not equal to -1. Take y to be x over x plus 1. Since x is not equal to -1, the denominator x plus 1 is non-zero, so y is a real number. Finally, we need to show that xy equals x minus y. To do this, we can either start with the product xy, substitute the definition of y in terms of x, then simplify to obtain an expression for x minus y. Alternatively, we can start with x minus y, substitute the definition of y in terms of x, then simplify to obtain an expression which we show to be equal to the product x times y. A third possible method is to show separately that the product xy and the difference x minus y are both equal to the same expression. We will start with x minus y and show that this is equal to the product xy. Observe that x minus y is equal to x minus x over x plus 1. This is equal to x times x plus 1 minus x over x plus 1, which is equal to x squared plus x minus x over x plus 1, which is equal to x squared over x plus 1, which is equal to x times x over x plus 1, which is equal to x times y. So, x minus y is indeed equal to x times y as required. Therefore, the number x over x plus 1 is the desired number y, which proves the existence of y. Since x is arbitrary, this proves that the claim is true. You have come to the end of this video. Before you proceed to Lecture 2.5, be sure to answer the exercises given at the end of these slides. Thank you for your attention.